Hello everyone, welcome to topic 8.1, Introduction to Acids and Bases. By the end of this, you should be able to calculate the values of pH and pOH based on the water ionization constant, or Kw, and the concentration of all species present in a neutral solution of water. There are several equations that will be discussed in this section of notes. All of these are present on your equation sheet that is provided to you on the AP test, so make sure you have it out and are using it. In Unit 4.8, the concept of acids and bases was introduced. As a reminder, a Bronsted-Lowry acid is a substance that donates hydrogen ions to solution. So when those hydrogen ions interact with water, it forms the hydronium ion, H3O+. Bronsted-Lowry bases are substances that can accept the hydrogen ion. When acids and bases are discussed, their pH is often referenced. pH is a way to describe how acidic or basic a substance is. pH is a mathematical manipulation of the concentration of the hydronium ions in a solution. To calculate the pH of a solution, you take the negative log of the hydronium ion concentration given in this equation. pOH is analogous to pH, and it is also found by taking the negative log but of the hydroxide ion concentration as shown in this equation. So we have several little notations, and all of these are referenced at room temperature or 25 degrees Celsius, where the pH scale is on a scale of 14. So this is also a common misconception that the acid-base scale is from 0 to 14. This is only true that the general scale is at 25 degrees C. However, you can have values that are outside of that scale or less than or greater than 14. For example, if you have a solution with a pH of 12 molar for like hydrochloric acid, that pH value is negative 1.079. So it can be negative, it can be a lot bigger than 14. It just depends on how concentrated that solution is. This is generally relevant, the scale of 0 to 14 that you may have heard of in a previous class, for strong acids or bases that are monoprotic, so they only produce one hydrogen ion or accept one hydrogen ion, and have a concentration of 1.0 molar or less. Okay, and that's just because of how the log scale, or taking the logs of things, works, because it's a base 10 system. The equilibrium constant for water can be written from the following reaction, the auto-ionization of water, and we'll get back into that in a second. Okay, at 25 degrees Celsius, the auto-ionization water constant for water is 1 times 10 to the negative 14, which is where we get that 14 base scale that is kind of a misleading thing. You may also see the simplified version of these using the hydrogen ion in place of hydronium ions as shown here. Okay, both of these work, however, H3O+ is preferred because it's showing that something is accepting that hydrogen ion. It's not just floating around in solution. So it's a completed process. You will only see the hydronium ion form, so this one, on the AP exam, so it is best to get used to using that in your work. Pure water is neutral because the concentration of hydronium ions is equal to the concentration of the hydroxide ions. So whenever you see pure water, it is neutral because of those two things. And this is due to the self-ionization or auto-ionization of water. It auto-ionizes itself, as discussed previously, and so when one water molecule takes a hydrogen ion from another water molecule, it's still going to produce the same amount of hydroxide and hydronium ions, like 1-to-1 ratio. We saw that at 25 degrees Celsius, the hydronium ion concentration times the hydroxide ion concentration was equal to 1 times 10 to the negative 14, which was the autoionization constant. We can solve and find that the concentration of both hydronium and hydroxide ions in this case is 1 times 10 to the negative 7 molar. Therefore, both the pH and pOH are 7. When we take the log of each side of the Kw expression, we find that the P of Kw is equal to pH plus pOH, and this is 14 at 25 degrees Celsius. This allows us to easily convert between pH and pOH as they sum to 14, but this is only true at 25 degrees Celsius, so you need to pay attention if it's giving you an alternate temperature. To summarize the mathematical relationships between pH, pOH, hydrogen ion concentration, and hydroxide ion concentration, there's this equation square below to help you start learning how to solve these. Okay. Just like other K values, Kw is dependent upon temperature. As you can see in the table below, as the temperature increases, the value for Kw also increases. Therefore, the concentrations of hydronium and hydroxide ions increase as well. It is important to note that water is still neutral even if pH values differ with changes in temperature. Water remains neutral because the concentration of the hydronium ions and hydroxide ions will remain equal for a pure water solution. There are some sig fig rules for pH, which I will review a little bit as we go through it. But generally, when we talk about pH, the significant figure digits are the ones that are always after the decimal. The one leading the decimal is not counted in the sig fig value. So if I have 3 sig figs here, when I calculate the pH, there should be 3 decimal points. And vice versa, if my pH has 3 decimal points, my hydronium or hydroxide ion concentrations, or even Ka, Kb that we will discuss later, will have 3 sig figs. Okay. As a reminder, when a substance completely dissociates or ionizes, it's considered a strong acid or strong base. The 6 strong acids are as follows here, where the sulfuric acid, only the first hydrogen ion is considered strong. Strong bases are the hydroxides from groups 1 and 2. This excludes beryllium and magnesium because they're kind of small and very densely charged. And we'll get into the why of those in a later section. Okay, so here. What is the molarity of the hydronium ion concentration in the following solutions at 25 degrees Celsius? Determine if they are acids or bases. Okay, so for this one, pH of 3.689. So if we look at the equations provided to us on the equation sheet, we would see that to find the hydrogen or hydronium ion concentration, that's a 3, we would take 10 to the negative pH value. Well, when we substitute in for the pH, we would see that this is 10 to the negative 3.689. Plugging that into your calculator, you should get 2.05. 3 decimal points gives us 3 sig figs. It's an exponential rule. I will say that on the AP test, remember that the FRQ is where you would see sig figs being counted for points, and there's only 1 point on the FRQ that is associated with significant figures. Okay? So, this would be our final concentration for hydronium ion, and then since this is less than 7, the pH is less than 7, this tells us that this is an acid. Okay, now if we have the pOH, okay, and it wants to still know the hydronium ion concentration, we need to figure out the pH first. Looking at this, we know that 14, and the equations given on the equation sheet, is equal to pH plus pOH. Okay, solving for pH, because that's the one that's going to give us or help us get to the hydrogen ion or hydronium ion concentration, we see that the pH is equal to 14 minus the pOH. rearranging the equation. Plugging in the POH, you should get that the pH is equal to 7.590. Make sure you're still using all the sig figs for the pH. Using the same equation that we did in the previous one, we would say that the hydrogen ion or hydronium ion concentration is equal to 10 to the negative pH. In this case, that is 7.590. Plugging that in, you get 2.57 times 10 to the negative 8 molar. Since the pH is greater than 7, we know that this solution is slightly basic. Just slightly, not by much, but it is slightly. Okay, finally we have the hydroxide ion concentration in C. Okay. There are a few ways to go about solving this. So looking at the equation sheet, I see an equation that says Kw is equal to the hydrogen ion concentration plus the hydroxide ion concentration. And since this is at 25 degrees Celsius, I know that that has to be equal, or Kw is 1.00 times 10 to the negative 14. Rearranging this to solve for the hydrogen ion or hydronium ion concentration, we see that that is 1.00 times 10 to the negative 14 over the hydroxide, because that will divide over. In this case, that is 1.56 times 10 to the negative 4. Solving this equation using a calculator, you get 6.41 times 10 to the negative 11 molar. Since the hydronium ion concentration is less than the hydroxide ion concentration, we know that this is a base because the OH is in greater concentration. Okay, so let's look at the we-dos. We have a solution of a weak acid, HA, with a concentration of 1.000 molar. The pH of the solution is 3.456. So this is an equilibrium reaction. So we're going to write the dissociation equation for this reaction. So HA as a weak acid doesn't completely dissociate. So we would say that HA, and it's aqueous, is going to react with water to partially dissociate into, and since this is an equilibrium reaction, we use the equilibrium arrows, the conjugate base plus the hydronium ion, because water is acting as the base and accepting that. Okay, if we write the expression for that, the equilibrium expression, everything that is aqueous is included, so products over reactants. Okay, now using the pH, we can calculate the hydrogen ion concentration, because we know that the hydronium ion concentration is equal to 10 to the negative pH. We know that the pH is 3.456. Plugging that into a calculator, this is going to be 3.50 times 10 to the negative 4th molar. And this is equal to the hydronium ion concentration at equilibrium. So once it dissociates and the reaction reaches equilibrium, this is the equilibrium. So I can put an EQ here so I know it's at equilibrium. Now we can complete an ICE table to find the equilibrium constant, or acid dissociation constant for this acid. So HA is going to be in equilibrium with the conjugate base and the hydronium ion. We know in the beginning that the initial concentration is this, and that these have not been created yet because it hasn't dissociated before it starts, right? And then this is going to decrease and increase respectively. And we know that at the end, that the hydrogen ion or hydronium ion concentration has to be 3.50 times 10 to the negative 4 so that we get the pH of 3.456. Well, that ends up telling us that that is equal to X, so I know that this has to be 3.50 times 10 to the negative 4 molar, and that this X is actually And so when I solve this process here to get my equilibrium for my weak acid concentration, I end up with this by plugging it into a calculator. Okay, so now I can find Ka. So I'm going to use part B to help me plug in for A. So my concentration of A minus, 3.50 times 10 to the negative 4, times hydronium ion, times the weak acid concentration, and then plugging this into a calculator because that makes everything so much easier. I get 1.23 times 10 to the negative 6 for my acid dissociation constant. Okay, so using the equation sheet and the pH, pOH, hydronium hydroxide ion equations, complete the UDOs. Check your work, and thank you for tuning in.